This is problem 746. It's on page 353. An ideal diesel engine has a compression ratio of 20. Write down this stuff as we go. R equals 20. And uses air as the working fluid. The state of the air at the beginning of compression process is 95 kilopascals, 20 degrees Celsius. Now, like I said, when you solve a problem like this, you should always be looking at the PV and TS diagrams. So see if you can find the PV and TS diagrams, and we'll just start adding to them. P, V, and we'll probably be talking about specific volumes again. And temperature versus entropy. Again, we'll probably use temperatures in Kelvin. Most of the time, that's how you do this. So what does it look like? Well, it looks something like this. State 1 is here, state 2 is here, state 3 is here, and state 4 is here. State 1 to 4, or state 1 to 2, just like in the Otto cycle problem, is the compression process. State 3 to 4 is the expansion process. 1 to 2, 3 to 4, both isentropic like before. The only difference is instead of having constant volume heat addition, we have constant pressure heat addition. So this is where Q in occurs. Q out is still 4 to 1. And the TS diagram looks exactly like it does in the Otto cycle. The key difference is that this upper line, so here's 1, here's state 2, this upper line from state 2 to state 3, while heat is being added, is a line of constant pressure. Before, both these lines were lines of constant volume. Okay? Anyway, that's the difference. So now we can add stuff. Let's see, the beginning of the compression process, what state would that be again? Beginning of compression?
1 to 2.
1 to 2 is compression, so beginning would be state 1. That's where they told us the pressure was 95 kilopascals. Temperature, 20 degrees Celsius. Well, if we put it in Kelvin, what would it be? 293 Kelvin. Okay, if the maximum temperature in the cycle is not to exceed 2200 Kelvin, well, where does the highest temperature in the cycle occur? You go look at the TS diagram and tell me. State 3. Absolutely. They get it? Absolute temperature? Absolutely. Bad jokes.
But does that mean that the max temperature is 2200 Kelvin?
That's right.
It is. So it's not just that it can't exceed that. That is going to be the max temperature.
That is going to be the max temperature, that's right. And it's always state 3, this is the maximum temperature in this ideal cycle. Okay, so we're supposed to calculate the thermal efficiency, mean effective pressure, and assume constant specific heats at room temperature. So in the interest of time, instead of going through and talking through this a lot, I'm going to just solve it. But what I'd like you to do is stop me and ask questions anytime I do anything that you don't understand or you wonder where it comes from, okay? So here we go. Most of the time the way we do this is we go from state to state. I'm going to begin at state 1 because I know everything there. The relationship between state 1 and state 2 is isentropic. Here's the most convenient equation because I have the compression ratio. Okay? So plug in the numbers, 95 kPa. 20 to the 1.4 power. It's not a surprise case, 1.4, right? We're using air like we did last time. So this pressure comes out to 6,297.5 kilopascals. A whole lot higher pressure than we saw in the spark ignition problem. 6297.5 kilopascals. We want to know the temperature. I'll use the ideal gas law to do that. P1 V1 over T1 equals P2 V2 over T2. Therefore, T2 is P2 over P1, V2 over V1, T1. You'll recognize V2 over V1 is 1 over R. And so T2 is 6297.5 over P1, which is 95, times T1, 293 Kelvin, times 1 over 20. Well, let's just do it this way. Over 20. Notice the kilopascals cancel. We'll just have a temperature in Kelvin. It's 971.1 Kelvin. So there's our temperature for state 2. Okay. The next step, go from state 2 to state 3. We're just going to walk around the cycle diagram. What do we know about the relationship between state 2 and state 3? This is the place where it's different from the Otto cycle, or the spark ignition cycle. There's something very important here that was not true before in the Otto cycle, and that is that the pressure in state 2 equals the pressure in state 3. They're equal. So we already know the pressure in state 3. That means it's going to make it very easy for us to deal with this problem. Okay, so let's use the ideal gas law and say P1 V1 over T1 equals P3 V3 over T3. Because then that will allow me to say that V3 is equal to P1 V1 over T1 multiplied by T3 over P3. Okay. Now why am I doing all this? Well, notice the only thing I don't know is the specific volume in state 3. You may say, well, what about the temperature? We know the temperature. That was the maximum temperature. That was the 2200. So state 3 was really easy. Once we had the pressure in state 2, we were done with state 3. Right? Because we already knew the temperature in state 3. The only thing that wasn't known was the specific volume in state 3. And let's see. Yeah. I was looking for the specific volume in state 1 because I don't have it yet, but I may not have solved for that. You don't always need the specific volumes. But to solve this, let's see. I do need the specific volume in state 1. In fact, I'll need calculator help because I didn't write it down. I use this as an intermediate result. So why don't you guys grab your calculators. What I did is I plugged in R T1 over P1 in here, did a bunch of cancellations, because you notice that T1 and P1 are opposite, so they're going to go away. Anyway, give me some calculator help if you would. 0.287, 287 or 278?
287.
287, I thought so. Kilojoules per kilogram per Kelvin is the gas constant. The temperature in state 1 is 293 Kelvin. The pressure in state 1 is 95 kilopascals. We will end up with cubic meters per kilogram because this is a specific volume. Of course, kilojoules are kilopascals times cubic meters, and so the kilopascals go away, and you can see explicitly that it's cubic meters per kilogram. So multiply 0.287 by 293 and divide by 95, please.
0.885.
Okay, thanks. So 0.885 will allow us to add another piece of data to our diagram. Notice if I had plugged in V1 here, V1R is R T1 over P1, it would look like this. We'd have R T1 over P1, P1s would cancel, the T1s would cancel, we'll just have R times T3 over P3 to get the specific volume in state 3.
So why didn't we use P2 and T2?
I agree.
Good question. Why didn't we use P2 and T2? We didn't have to.
So it's just we could have used either.
Well, we're at state 3, so it would be ideal to use that. But why did we go for 1 instead of 2? Well, mainly because I knew I need the specific volume in state 1, and I knew I could get it to cancel, so that's why I used it.
Did we not?
But you could have equally well have used P2, T2. The problem is you need the specific volume in state 2, and then you'd have to solve for it. You could do it, right? Because you already have P2 and T2.
So in this diesel example, we can jump.
Yes, you can. Yeah, absolutely. You can relate state 1, 2, 3, and 4, just like we did in the Otto cycle, because it's still a captive mass.
You told us to walk, not jump around in the Otto cycle.
That is true, and I'm trying to show you where you can break the rules if you need to.
Okay.
Yep, good question. Now, when I say you walk from one state to the next, generally you can use this to jump around anywhere you want. It's the other things that are important, like state 1 and state 2 is related isotropically. You can't jump from state 1 to state 3 using any equation, right? Yeah, you can use this, but usually it doesn't help you, right? That doesn't help you until you already have used something else. So far what I've done is I've used the fact that this is an isotropic move and this is a constant pressure move. Okay, I've used those two pieces of information. Then I can use this ideal gas thing any way I want. Okay, good question. All right, so now let's continue. We need the specific volume in state 3. You can see how things cancel. You know R, you know T3, you know P3. Plug in all the numbers. You'll find the specific volume in state 3, and it is 0.101. Now, for the sake of completeness, even though I didn't do it in my solution, why don't we solve for the specific volume in state 2? You guys brought it up, so it's a good question. In fact, we could do it by simply saying, well, let's see. What's the easiest way to do it? We don't know the mass, so
Can't we just use P1 and V1 over T1 to?
yeah, that's the easiest way. P1 V1 over T1 equals P2 V2 over T2. And I don't think it's in my notes. There's something I want to show you guys. Well, I tell you what, I did this later. Let's go ahead and do it now so we can add it to our diagram. That's one way we could do it. Another way we could do it is V2, just the ideal gas law directly, R T2 over P2, right? Because we've got T2 and P2. But I wanted to show you guys the cutoff ratio and how it's related to a temperature ratio. And I don't have that in my notes here. But we'll get that in a minute. Let's get this done and we'll finish off. So this would be the gas constant, 0.287. I'm not going to add any units because it will just come out to cubic meters per kilogram just like I did before. T2 was 971.1 Kelvin, and P2 is 6297.5. And when you plug all that in, you find that the specific volume in state 2 is about 0.044 cubic meters per kilogram. Okay, so now we've got all of these. Now, before we move away, there's a very interesting relationship for the cutoff ratio, and I want to develop that quickly so that you can see. I had you write this down when we were going through the diesel cycle in your book, but I want you to see where it comes from. The cutoff ratio, R sub C, is defined as, so I should use a triple equal sign, as the volume at state 3 divided by the volume at top dead center. Okay, the volume at top dead center is this V2. Okay, now I don't have this in my notes, so I'll have to work it up. But I want to show you how this is just the ratio of the temperatures in the two states. Okay, notice that V3, V2, V3 would be equal to R T3 over P3, right? Okay, and V2 would be R T2 over P2, right? The R's go away. Notice P3 and P2 are the same thing. And so this is T3 over T2. So if you wonder where that equation came from that I gave you, when I had you write down that the cutoff ratio is just T3 over T2, that's where it comes from. Okay? I wanted to show you that before we moved on. Okay. So what do we got? Well, we've got all the way to state 3, so now let's go for state 4. I'm going to move from state 3 to state 4. Notice if I had Q out, I'd move from state 1 to state 4 by an energy balance. Kind of like playing chess, you know how the moves go. Okay? You just got to get used to the moves in these problems. So if I want to relate state 3 to state 4, an isotropic equation is probably the easiest way to do it. In fact, it's the only way I know to do it. V3 over V4 to the K. And notice that this is the same thing as V3 over V1 to the K, because V1 and V4 are the same thing. Okay? Now, I want to develop this a little bit farther because I want to include the cutoff ratio and the compression ratio, because this is something that's valuable for you to know. The cutoff ratio, remember, was V3 over V1, right? No, that's not the one I'm looking, no, not V1, V2, sorry, because it's the volume at top dead center. The compression ratio, R, is equal to the volume at bottom dead center. What am I doing here? I want to make sure I get a number larger than 1. So, yeah, bottom dead center, V1, over V2, yeah, volume at top dead center. Notice that if we want the ratio of V3 to V1, we can get it by putting these two together. See how I need V3 over V1 here? It's handy to know this. Sometimes you don't want to go through and take the time to calculate the specific volumes because they're not all that useful, okay? So here's one equation I want you to add next to your diesel cycle diagram. Notice if I take RC over R, I would get V3 over V2 divided by V1 over V2. You see how the V2 cancels? And you just get V3 over V1. So notice that this is simply, let's do it this way instead of crossing it off. This is simply RC over R to the K. So what I want you to write down is that P4 over P3 for the diesel cycle only is RC over R to the K, because it's a handy equation to have. And you might put it next to your cycle diagrams for the diesel cycle. What's that?
So P4 over P3.
P4 over P3 is the cutoff ratio over the compression ratio to the K, to the power of K. We'll go ahead and use that. You can look at my solution later. I use the pressures and temperatures in the states, states 1 and states 3 since we have them. But you'll get the same result. Everybody have this? Okay, so what you need is P4 over P3 equals RC over R. Because I took the ratio of RC over R, V3 over V2, over V1 over V2, the V2's cancel, I get V3 over V1. Okay, so far so good? All right. So anyway, like I said, I used the temperatures in states 3 and 1 to come up with those. Obviously now we have the volumes, we could use those. It really doesn't matter. Any way you want to do it, it'll work out the same. And so you can solve for the pressure in state 4 as the pressure in state 3 times RC over R to the K. When you do that, you find that it's 298.5 kilopascals. So there's the pressure at state 4. So let's pull that off over here, 298.5. Now what about the temperature? Well, we can get the temperature in state 4 pretty easily. The temperature in state 4, let's do it this way. Let's use the ideal gas law. P1 V1 over T1 equals P4 V4 over T4. Why wouldn't I go from 3 to 4? Because I know that the volume in states 4 and 1 are the same. So that way those specific volumes just go away. Makes it a little easier. And so now the temperature in state 4, if I solve for it, is P4 over P1 times T1. And plug in all the numbers, well, I'll plug them in here, it doesn't take long. 298.5 over 95 times T1, which is 293 Kelvin. And you find that the temperature in state 4, let's see, right here, is 920.6, just barely below the 971.1. Okay? Now we're supposed to find the thermal efficiency. We didn't have the cutoff ratio from the very beginning. We can get it now that we've got the volumes. So probably from the given information, the quickest way to get the thermal efficiency is to take 1 minus T4 less T1 over the over the ratio of heat capacities K times T3 less T2. Notice this is the thermal efficiency, because that's what we had when we plugged everything into the slides. That's what we came up with. It was that equation for efficiency. It's not the only one. We could also plug everything into the equation that involves the ratio, the cutoff ratio and the compression ratio. So we can get at that too now, but we're not trying to beat this problem to death like we did the auto problem. We've got all the temperatures, we may as well use them. So this would be 1 minus, and then T4 is 920.6, T1 is 293. The ratio of heat capacities is 1.4. T3 we found, or that was really given as 2,200. And we found T2 as 971.1 Kelvin. So plug all this in, you find an efficiency of about 63.5%. That's one of the things they asked us to find. Okay? We're not done. They also wanted the mean effective pressure. Any questions so far, though, before I go on? Okay, let's get the mean effective pressure next then. Tell you what, you guys are sitting there writing. I'm going to engage your brains again. Give me the equation for mean effective pressure. How does it go?
It's work done over specific work done over displaced volumes and the
Yep, V min, V max. So V1 is V max, V2 is V min. Okay, so that's just the displacement specific volume. How about the net work? We don't have the net work, do we? But we do have the efficiency. And remember, efficiency is net work over Qn. So couldn't we say that this net work that we want is just thermal efficiency times Qn?
Yeah.
We can do that. Doesn't seem like much fun though, does it? Because look, we've just substituted one unknown for two, but oh well. Well, why would I want to do that? Well, I know the temperature change from state 2 to state 3, right? And I also know that what happens here is a constant pressure process. And so I know that Qn is equal to the heat capacity times the change in temperature between states 2 and 3. How do I know that? Well, remember in the diesel cycle problem, when we needed to approximate when we needed to calculate Qn, we did it by combining the boundary work with the internal energy change. Let me go back a slide so you can see that. Remember we went through this whole process where we said Qn for the process from 2 to 3 minus the boundary work, because remember the piston's moving down while heat's being added, is equal to U3 less U2. But that boundary work is the boundary work of the constant pressure process, so we can move it to the other side of the equation, combine it with the internal energy change, and come up with the enthalpy change, which is just a Cp delta T term. Okay? So that's why I can write Cp delta T instead of Cv delta T, because Cp will include not only the energy that's deposited in the air, but also the boundary work the piston does as it moves down. So that accounts for both of them. Okay, so let's plug in the numbers. We know the thermal efficiency is 0.635. Qn is Cp, which is 1.005 kilojoules per kilogram per Kelvin. T3, let's see, that was 2200. T2 was 971.1, and that's Kelvin, so the Kelvin go away. Divided by V1 less V2. Now V1 was 0.885, V2 was 0.044. The units there were both cubic meters per kilogram. Kilograms go away. Kilojoule is a kilopascal times a cubic meter. Cubic meters go away. We have kilopascals, which is appropriate for a pressure. In fact, it comes out to 932.5 kilopascals. Whew. Still alive? Questions? By the way, these are the simple cycles. Once you get to 320, we'll make these a little bit more accurate and improve them. You may not think of them as an improvement, though, by the time you get there. We'll see. You'll laugh at the 220 students and say, oh, that's the easy stuff. What's the matter with you guys? Good to know. Any questions?